To introduce our next plenary speaker, Professor Lloyd Hollenberg from the University of Melbourne. So Lloyd is a Melbourne Laureate Professor and an ALCS Laureate Professor and the Thomas Baker Chair in the School of Physics at the University of Melbourne. He is the Deputy Director of the Australian or ALCS Centre for Excellence for Quantum Computation and Communication Technology, and he also directs the IBM Quantum Hub at the University of Melbourne. So he's presenting on linking quantum computing with HPC.
Thank you for the introduction, and to the organisers, Sean and the team, for the very kind invitation to come here and speak about quantum. So yes, what I'd like to cover is quantum computing in the HPC nexus, and we heard a little bit this morning from Rick about how that connection could play out. But before that, I thought I might do just a bit of an overview of quantum computing and where we are at the moment. So a lot of people say we're actually now in the second quantum revolution, and you're probably thinking, wait a minute, what was the first one? So the first one, actually quite familiar things like MRI machines. That's where you're effectively doing kind of quantum measurements over billions of protons, and that's been fantastic technology, and it is undeniably quantum at the very heart of it, but it misses out on a lot of key aspects of quantum mechanics that we can now harness in this second quantum revolution. And this is generally that we have control over individual quantum systems, and they may be things like atoms, nuclei, electrons, photons, or even little superconducting circuits. If they exhibit fundamental quantum behaviour, things like superposition, entanglement, measurement, all these sort of weird quantum effects, and you can harness those effects in new properties or functionality, that's what we really talk about when we talk about quantum technology. And the three pillars of quantum technology, which kind of overlap a little bit, quantum computing, quantum sensing, excuse me, and quantum communication. And I'll be focusing mainly on quantum computing, but sometimes I won't be able to help myself and I'll just talk about quantum technology. So it would probably take a good half an hour of my allotted time to go through quantum computing and how it all works. So let me just summarise in half a slide. So if this is what we call a classical NOT gate, so in quantum information technology, anything that's not quantum we call classical, so sorry about that. The quantum version does the following. So the quantum version of a NOT gate is actually an X gate for mathematical reasons, but it's just a gate that flips the bits, but it does it in an inherently quantum way. So what's presented in general to a gate like this in a quantum computer is a combination, a qubit state that could be a combination of 0 and 1 in a quantum superposition. And here I've just sort of indicated that associated in that combination are probabilities of where, you know, if you measured that qubit at this point in time, you'd have a lower probability of measuring a 0 than a 1 in that particular state. So what a NOT does in a quantum sense is to flip those probability distributions around. You can view it as flipping the 0 to a 1, or you can view it as swapping the complex amplitudes that dictate those probability distributions. And then there are general gates. There are more single qubit gates than that, and there are 2 qubit gates. And that builds up our whole repertoire based on a universal gate set for building any mathematical computation we want to do over those binary numbers. Okay, so when people talk about, well, what sort of things can a quantum computer do and the sort of speed ups and so forth, this is probably a woefully inadequate Venn diagram, but nevertheless, a big blob of classically hard problems, and within that is the class of classically easy problems. So a quantum computer doesn't make everything easy. It makes some things easy in the sense like factoring, which is thought to be exponentially hard with the size of the bit string. It can make that polynomial, so that becomes easy in that sense. But a lot of other problems don't become easy, they become easier. So it's more like a polynomial speed up. And so that's why I've sort of tried to indicate it like this. And I've projected it out the side there because there are some areas where we're not quite sure what quantum complexity class we're talking about, and things like quantum machine learning may do things in a totally different way. But nonetheless, the main message I'm going to be talking about today is, yes, quantum computers do things differently. However, we are most likely, very likely, probably certainly going to have a lot of HPC associated with the sort of quantum computations we want to do. So where are we at the moment? Well, the best overall in the world is at about 100 qubit level, which may not sound a lot to you, but you know, when I started some 25 years ago in this area, there were effectively 0 qubits really in terms of control. So for me, this is quite amazing that systems have got to this size, but it's not just the number of qubits, and I know people focus on that a lot. It's really critical how good those qubits are and how good those logical gates are, because that dictates what you can ultimately do with these machines. And it's really not so much the number of qubits now. We almost have too many qubits. We just don't have enough precision. So precision at the moment, pretty much around the 99% level is really the best. Google in their supremacy result, which I'll talk about in a moment, are at the sub 1%, probably about 0.5% precision. On the software side, there's a lot of work in that confluence between quantum physics, computer science, and end users in terms of trying to figure out what can you do with a quantum computer now, in the near term and in the longer term, and I'll talk a little bit about that. So the state of play is kind of the following. There's this quantum supremacy result, which you might have heard about. That was the Google machine based on superconducting qubits, 53 qubits, and basically the mathematical task that it was comparing against HPC was to simulate itself running random programs. So they would literally program it with a random program of varying depths, 53 qubits and a certain length of the program. And the task was to run it enough times to get the probability distribution as the output, because as I was indicating, when you measure these things, there are probabilities involved, and so really what's key when you run a quantum computer program is to determine that probability distribution. And then compare that, so you're running the random program on the quantum computer, running it against then the simulation of that quantum program on, as it happened, IBM Summit. And the original claim by Google in 2019 was that they could obtain data on a 53 qubit random program in 200 seconds that would take Summit some 10,000 years. And then IBM shot back even before the Google paper was published and said, well, actually, you know, you're not using the memory properly and you could do it in 2.5 days. And I should say, look, I'm not a HPC expert, so I didn't quite understand all that. But to me, the fact that there's still this big disparity between 200 seconds and 2.5 days on a machine like Summit was really something quite special, and it's a really great paper. That's been followed up in 2020 from USTC, a different type of quantum computer. It's a photonic-based quantum computer of order of 100 qubits or so, running what's called the Gaussian, running the problem enough times on the quantum computer to get a distribution out the back, and then comparing that with, in this case, Fugaku, and their claim is 600 million years to get the same level of data. So I imagine that's going to be picked apart as well. But these are quite audacious and very interesting results. So where are things at the moment? As I said, we're at about the 100 qubit level in terms of fairly good precision, but we're reaching towards the 1,000 qubit level in terms of what you can actually build. So IBM have a roadmap and indicates in 2022 a 400 qubit machine, which they've delivered effectively, and they're heading towards 1,000 qubits. But as I said, it's not just the number of qubits that's important here. Okay, just a quick snapshot of what's happening around the world. I don't want to take too much time on this, but there's a lot of activity, a lot of initiatives around the world in terms of creating large-scale initiatives around quantum computing, including not just gathering people together in centres, but sovereign installations in various countries. This is an interesting plot from Simon Devitt that was published in the ASPE report, showing how the startup activity has just really exploded over the last few years. This is a plot of hardware, software, startup corporation, and you can see startups are really getting involved, especially in the software space. So it's a very interesting time. IBM has very early on, 2018, developed their IBM Quantum Network, of which we're a part as a hub down in Melbourne, so we were able to access their latest and greatest machines. There are quite a few of these hubs around the world and a lot of members that are then part of this network as well. And other vendors are doing similar things in terms of garnering activity. So the generic sort of priorities that people look at in any country are to develop quantum hardware capability, quantum software, and workforce training. And in Australia, we're doing that in various ways, and there's starting to be some coordination, as you've probably heard, the CSIRO report on the potential of quantum technology, not just quantum computing, but this is now broader quantum technology. And more recently, the National Quantum Strategy paper came out, and there's been a string of funding announcements after that. The Australian position in quantum is actually incredibly strong, and you can pinpoint that to the ARC Centres of Excellence, I think. Not just because I've been part of CQC2T for 20 years or so, but you can really see that some of the academics that have gone on to bigger and better things, not just in Australia, but around the world, really came out of this Centre of Excellence scheme from a number of centres that have been working in quantum in some way. So I think it's been a real testament to how well that scheme works to give people scale of collaboration and longevity of funding. That's been really important. There's quite a few startups now in Australia, and I apologise if I haven't captured all of those, but some are in the hardware space, some are in the software. There's a lot going on. Okay, so let me get to the nub of what I really want to talk about, and that's what we do on a quantum computer and what we think we can do in the future. So this is typically the way that people plot where quantum computer technology is. So along here on a log scale, the number of qubits, and up there is the really important error rate of the machine itself. It's called the C0 gate. It's how two qubits actually interact with one another. And that's a very hard interaction to organise in nature, because nature likes symmetric interactions, and this is a very asymmetric interaction. It's a controlled knot. You flip the state of one qubit based on whether the control qubit is a 1 or a 0. So that error rate is currently around about the 1%. We'd like it to get below 0.1% in order to perform quantum error correction down the track when we have enough qubits, and Rick was alluding to that earlier, that every qubit in this phase, if you're doing quantum error correction, every qubit in your algorithm is actually maybe 1,000 or 10,000 physical qubits that are doing their stuff, and I'll go through that a little bit later. But basically, we're in this sort of phase here, and this is where error rates are around about the 1%. We've got a fair number of qubits, but this is the noisy intermediate scale quantum regime, or NISQ. And so you hear a lot about, what can you do with NISQ machines, as opposed to the fault-tolerant quantum computing regime. So fault-tolerant quantum computing means that you're doing quantum error correction, and you're not just correcting faults, but you're doing it in a way that you can actually, handle with that particular error correction code. And so this regime here, if you're below that threshold, you effectively have incredibly low error rates on your quantum components. All of a sudden, a whole vista of quantum algorithms open up to you. But the trouble is, in order to get that sort of suppression of errors, you need massive redundancy. So at that level, you really have millions of physical qubits, and you have to connect them up all in the way to do quantum error correction. To my mind, the big question is what happens in the intermediate regime where we have a lot of qubits and our error rates are well below 1%. Can you actually do anything useful? And this is what I would call the heuristic and approximate quantum computing regime. Is there anything that we can do that's useful there, and in particular on a real world problem? So this is the whole question of quantum advantage. Okay, so here is an example, just to do a very quick deep dive, and we'll come up for air in a tick. So this is a quantum circuit over 6 qubit. It's actually from a quantum chemistry problem. It's setting up the trial state for a chain of 6 hydrogen atoms. And you can see the problem immediately. That's a fairly small chemistry problem, but it's a pretty complicated circuit. It's got 27 of those C0 gates, those 2 qubit gates. And if you had 0.5% error, a rule of thumb would be that the output fidelity, if you just counted up, would be something like 90%, which sounds pretty good. But for chemistry, you need very precise results. You need something like 3/9% in order to achieve chemical precision. And so already you have to think, if I'm going to run a program like this, which you can on these machines and get sensible output, but if you want output that's at chemical precision, you need to start thinking immediately, how do I mitigate errors? How do I change the strategy on how I compute, what I'm computing, in order to get the best that I can out of this machine? And I can tell you can get very close to that 3/9 by applying a whole plethora of techniques that people have started to think about and create by virtue of the fact they have the machines there and they're trying to get the best results out of them that they can, probably because their institution is paying for access and so forth. So it's a very interesting era that we can program such things, but it's really all about that creativity to mitigate errors and get the best that you can out of it. So this is IBM's latest. This is the Osprey chip, and I think the machine's called Seattle. It was announced late last year. We've been playing around with that now because, as I said, we're one of the network hubs and we have access to them. It's not quite 433 qubits. When they map it out and they've tuned up all the gates, there are a couple of dead regions. There's a few qubits here that don't work. There's a little region there, and I think 333 doesn't work. And so it's actually 414 qubits, but that's still pretty impressive. So that's a lot of qubits, and if you want to just do a count of how many how many 414 binary strings you could represent in a superposition, it's 2 to the 414. That's a pretty big number. But the trouble is the error rates are pretty high. So typically the new machines that come out have a lot more qubits, but the error rates are pretty high. It takes a long time then to tune and get these things better. So for our mind, it's the previous machines at about 127 qubits that are really of much more interest because they have much better error rates. Okay, so finally, let me talk a little bit about how HPC intersects with quantum computing. So there are a number of ways this happens, but I was only ever I'm going to talk about 3, and you can ask me questions about the other ones. I'm not sure how much I know about them, but first of all, the hybrid approaches. And again, Rick alluded to these this morning. So let's have a look at that. Typically, we might be presented with a problem in the form of a graph, and that could be an optimization problem, a traveling salesman problem, or even a chemistry problem in the sense of how the interactions are happening between the atoms. And what happens in this problem flow is you start with that problem like this as a graph, and there's a well-defined way to map that onto a form of problem. It's like an Ising model type problem that's very suitable for basically translating to a cost function that you can calculate on a quantum computer. Okay, and then what you do then, you set up a parameterized quantum circuit, which in some way is related to the ground state of the problem, and you may not know that to start with, so you parameterize it with a bunch of variables. And then you measure the cost function on the quantum computer. This is where it sort of does its 2 to the n type thing. And then that cost function, that goes to some optimizing routine, and that's typically where HPC would come into play as the number of variables in that quantum circuit increase in order to get a good solution. And so that loop has to go around many times until it converges. And then what you get at the end of the day is an optimized cost function and also the configuration of the system that corresponds to that cost function. Okay, so this is how we do it at the moment. And so here we are at our IBM hub in Melbourne. We send our quantum circuit as a job to the queue, and it's all on the cloud, so it's very convenient. It sits there for a while, depending on how much of our daily allocation we've used up. And then we get the results, and then we put it into the HPC and then do it again. So it's very laborious doing it that way, and IBM realised that that was a challenge. So what they've done is instigated a runtime version of Qiskit, which allows you to set up the job as one that you submit, and it will do all that loop of HPC, minimising over the parameters. So that's kind of a step forward in terms of making those calculations a little bit more convenient. So let me give you an example of one of these kind of hybrid approaches, and this one is particularly suited for chemistry type problems. It's called the variational quantum eigensolver, and it was thought up back in 2014 in a very simple sort of photonic or very simple chemistry problem set up with photons. And the lead author, Alberto Peruzzo, is at RMIT, so it's a great Australian connection. And the idea is that you would set up a trial state which is your best guess to the answer to your system. So it's very much like the variational method in quantum mechanics. In fact, it is. So there's a trial state circuit, represents your system with a set of parameters. You measure its energy, and you then start doing this sort of HPC minimization loop on those results, and you keep cycling around until you find the lowest energy. So if this is your sort of trial state variation in sort of this 1D of those many variables, if the solution's here, you want to find the minimum of the expectation value of the cost function, which in this case is the quantum Hamiltonian. The trouble is, yes, you might introduce more and more parameters and get closer to that, but that will only work when there's no noise in your calculations, your estimation of the energy. As soon as you have noise in there, that minimum goes up, okay? It gets you further and further away from your solution. So that's one of the big challenges here. So here's a case in point. There's been many demonstrations of this, but I'll show you one of the ones that one of our students, Harish Valluri, did. And that's on this so-called Heisenberg model. It's basically 20 spins that interact in a quantum way. This is the interaction. You don't need to know any of that, except that what we're trying to do is find the lowest energy of that. And it is known exactly in 1D how to do that, but it's a great test bed for calculations. And so here is a quantum circuit over 20 qubits, and basically each of these green layers has a bunch of variables that are your parameters to minimize against, and then you would add more and more layers, okay? Now the trouble is, as you increase the number of layers, it's great, more parameters, you're sort of getting a much more accurate representation of the actual ground state, but more layers means more gates and more noise and errors. So this is what happens. So if you simulate this with no noise, so we just run this simulation on our various clusters, you can see as you increase the number of layers, you're generally converging down to the exact result, which is that dashed line, which is great. But that's just the zero noise case. Now, when you run it on an actual quantum computer, this is what happens. So here is the exact down here. And as you increase the number of layers and make that circuit more complicated, it basically strays away until it gets to a high temperature limit where you're just getting random stuff out. So this is really, in a nutshell, one of the issues with NISQ devices at the moment. You want to be able to program deeper and deeper circuits, but you get more and more noise, and you have to deal with that. So one of the ways that we've been looking at dealing with that is via what's known as quantum computed moments. So this is a technique that I thought up quite a few years ago, just before I got into quantum computing, is one of the reasons I did. And that is to compute not just the expectation value of the Hamiltonian, but powers of the expectation value, because that introduces much more dynamics of the problem into what you're actually measuring. So it's the same sort of thing though. You would set up a trial state, measure these moments. There's a whole lot of classical computing that you have to do associated with that. And from those moments, even just using the first 4, you plug it into a bit of maths and you get an estimate out for the energy. Okay, don't worry about any of that. But some of the interesting things that we need to do along the way is if you take that Hamiltonian, and you can see it already for this 20-qubit problem, there are going to be a lot of terms in there corresponding to all the interactions. If you then raise that to the power of 4, you have a large number of terms, and you have to sift through that for all the unique terms that you would eventually measure on the quantum computer. And that's basically called this tensor product basis set. So as you increase the number of qubits in various problems, you see that grows very quickly, that h to the 4. But the actual number of terms that you need to measure on the quantum computer is actually quite reasonable in terms of how it scales. But the challenge, the HPC problem there, is to go from this down to that. It's a highly non-trivial sorting problem. So that's one point where HPC comes in. But the thing that happens then, when you compute using this moment method, instead of the results just going off away from the exact, you get this orange curve, and you see that having more information being extracted from the quantum computer in terms of moments has improved the result quite markedly. And you actually get this one point there, which we think may be actually what we're dreaming of, which is that hack solution. But the point I want to make is that we've put in much more classical computing to do that sifting through the things that you measure. And so how does this scale in terms of the balance between what you're asking the quantum computer to do and what you're asking HPC to do? And it's actually non-trivial to sort all that out, and that's one of the things that we're trying to do now. Okay, so the second area that I'll touch on is basically that area that underpins supremacy and whatnot, and that's simulating quantum circuits. And so I'll split it into 2 classes. So one I'll call inherent, and that's where you're just simulating a quantum circuit. So in the case of Google Supremacy, they had random circuits and they just simulated those on the supercomputer that they had. And there you can see, well, how faithfully does an actual quantum computer with errors compare with the simulations? And typically the simulations would have no errors, but often you want to actually incorporate errors in the simulations to see if you're understanding things properly. And then another case would be an instance where you want to know, well, given a particular quantum computer algorithm, how well does it solve a particular problem compared to what you can do classically? Obviously, we're still at the stage where the problems are relatively small, but eventually that will bring in HPC on that question. Okay, so what's involved in the simulation of a quantum circuit? Well, to store a quantum state, so as I said, if you've got n qubits, you've got 2 to the n different quantum state, different strings of 1s and 0s that can be basically represented in the quantum computer and in superposition, so effectively represented at the same time. Now, each of those 2 to the n states is really represented by a complex amplitude. So the amount of storage is 2 to the q by 2, because they're complex, by say 8 bytes. Okay, so that starts to get quite large when you get up to 100 qubits or higher. So an example of this is the system that we developed back in 2016, as it happened, to underpin our teaching in quantum computing at Melbourne Uni. And so this is our little quantum user interface, our QE system. You can just sort of play around with it there. And basically you're creating a circuit here, and then when you hit compute, it sends that circuit, and we've set it to less than or equal to 10 qubits to keep it manageable. And that just runs a simulation of that circuit and then sends all the results back, but importantly at every time step, so the students can then just sort of go backwards and forwards through the circuit and see what happens. So that's a very simple test case of when you need to run a circuit in teaching. But it really became important when they were talking about these quantum supremacy results. So particularly in the Google result was all about, here we have these random circuits, 53 qubits and a certain number of time steps. We simulate that and try to get the probability distribution at the end of that to match what you can get on the physical device. So it's all about simulating the quantum circuit. And a similar thing is happening with the Gaussian boson problem. It's basically running that particular problem to get a certain amount of information on the sampling distribution. So that is definitely one area where HPC is, I think, being quite, tested quite a bit by quantum computing. It's in understanding what people are doing now on these larger machines. And one instance where we were playing around with this is in just understanding Shor's algorithm. So Shor's algorithm is a factoring algorithm. So if you look at P times Q gives you, so P and Q are prime numbers, multiply them together to get a semi-prime. That's easy to do, even when the numbers are really big. You can put that in Mathematica or do it in a microsecond or something like that. But if I give you n, and it's a big number, and I ask you to find P and Q, the prime factors, that's a hard problem, obviously. It underpins RSA and so forth. So Shor's algorithm is a way of doing that in exponentially better time than any classical program that we know. This is one incarnation of a circuit for Shor's algorithm in schematic form. It's basically a period finding algorithm. Shor, really the genius was to convert semi-prime factoring into finding the period of a modular exponential function. That it means, well, when you find that period, you can relate it back and get the factors P and Q. So that's what this is. It's a period finding algorithm, but applied to that problem. And what happens when you run that, so for a L-bit prime number, you need 3 L qubits, and the task is based, well, when you run it, if it was done on a perfect quantum computer, you would get these very sharp peaks out at the end. And so when you measure your state of that register, you're highly likely to get one of the integers corresponding to these peaks and nothing else. Okay, and the thing is, it's all set up so that any of those peak numbers that you get out gives you enough information to extract the factors. Okay, so in terms of a simulation problem, we had a look at how hard this is to simulate as a function of number of qubits. This was done by one of our students, Aidan Dang, and it was back in 2018-19 on one of the Pawsey machines. And this was a 60 qubit problem. So you can imagine 60 qubits, well, you can work out that would have been a lot of memory, but you don't have to simulate in that particular way. You don't need to know all of those amplitudes in order to simulate an algorithm like this. There's a very clever way that was developed a few years ago called matrix product states, where the simulation naturally truncates according to how much quantum entanglement has been generated. And it means that you can handle these sorts of circuits where you've got a lot of qubits and you would have had too many states to store. The amplitudes would have been, you would have had too many to store, but you can simulate them according to an entanglement truncated method, MPS. And it meant that we could basically factor that number, which is an L equals 20, and this is how much of the resources it took to do that. But the amount of memory was far less than naively you would have thought for a 60 qubit problem. Okay, another way that we use quantum simulation of circuits is in designing circuits now. So one of the big problems, again alluded to this morning, was when people think about quantum computing, they often think big data. That's going to be fantastic. I can sort through my data polynomially faster at least. And one of the first algorithms I came up with back in 2000 was for bioinformatics to do sequence alignment polynomial or quadratically faster. But of course, one of the big issues is you have to take all of that data and load it into a quantum register. You have to put it into a quantum superposition. And nobody really knows how to do that efficiently. You can do it exactly, but you end up with these incredibly long circuits that you would never be able to run on a quantum computer because they take too many time steps. So one of my students, Lloyd, has come up with a genetic algorithm which basically has a population of circuits and does all the genetic evolution on those to produce circuits with better fitness to encode particular functions. So here is a Gaussian that's been encoded on the qubit labels. And these are the amplitudes that you're basically encoding. And the genetic algorithm circuit the genetic algorithm produces highly compressed circuits compared to what Qiskit would produce. So we think this could be a really promising way of starting to load data into a quantum computer within reason, because ultimately you would have to do this, firstly on a HPC system in order to simulate these circuits. But we think that we can simulate circuits up, between 30 and 40 qubits on a big system. And to be able to do this evolution and this circuit construction for a meaningful amount of data, that would be very exciting if that worked. Okay, so the last topic will be quantum error correction. So the way quantum error correction works is actually quite interesting in its own right, because if you think about a single qubit sitting there in its little superposition of 0 and 1, if you measure that to find out anything about it, it will collapse to 0 or 1. So you can't get any information out in terms of, is it faithfully storing your data by measuring it, by looking at it, and that's how we would do things classically. So people thought for a long time at the start of quantum computing, because there was no error correction possible with the collapse of the wave function, all the rest of it, you could never do anything on a quantum computer. Decoherence would always get you. But again, people like Shaw and Bacon and Steen came up with very clever ways to do this. And this is basically how it works. So imagine you encode your quantum information not just in one qubit, but in a group of qubits, a group of data qubits. Now, you never want to measure those, because if you measure them, their quantum state collapses. There is something called a no cloning theorem. You can't clone a quantum state, so you can't copy what that state is. But what you can do is you can basically provide an ancilla group here, a summary of what that particular quantum state is. You can do CNOTs from the data qubits to the ancilla qubits, which don't change the data but change the ancillas, in such a way that if I now measure the ancilla group, it will tell me if an error happened on the data qubits. And you can then come in with your quantum control and do an operation to correct that error. And you can do that without measuring the data qubits. So it's very clever the way it works. But the thing is, to get this really working in practice, we'll require data qubits much more than that 7. You would need thousands of data qubits and thousands of ancilla qubits. This is where things blow up quite a bit. And so what you're going to be presented with, if you have that on your quantum computer, every time you run a quantum error correction cycle, in measuring the ancilla qubits, you get what's called the error syndrome. And if you imagine I have a 2D array of qubits, and it's a checkerboard, so one colour are the ancillas, the other colour are the data qubits, basically. You're measuring ancilla qubits all over the place, and you get these patterns of things that have happened, various errors that the ancillas say have happened in my immediate region. Now, the thing is, the way these error correction codes work, you can't directly translate that to, oh, this is the correction I do on the data qubit. You have to do quite a bit of processing of that syndrome map in order to figure out what are the corrections to make. So the process is going to be, I have a massive 2D array of qubits, and it would be millions of qubits. And every cycle of my error correction, I get a picture like this out as my syndrome from measuring the ancillas. And then I have to process that very quickly to decide what I do to particular qubits to correct the errors that have occurred. So that's becoming a really big issue, even though we haven't got such systems yet, but to figure out, well, how do you do that classical processing step? So one of our students has been working on this, and this is an idea that other people have been working on too. It's basically using some form of machine learning on these types of pictures because they all basically have the same sort of primitives involved, and you have to then stitch that all together. And he's been able to take systems of the order of millions of qubits, and by sort of overlapping patches and whatnot, do the processing that's required pretty quickly. But the thing is, if your clock speed of your quantum computer is nanoseconds or even a microsecond, you have to do that really quickly. Okay, so that's all I think I have time to go through, but there are lots of other areas. So number 4 would be, well, something that we also heard about today, things like using AI to even optimize our programs that we write on these systems. I think that's a really obvious one, and I think people would be doing that if not already. And people use machine learning for controlling their systems, actually controlling the hardware, which is really interesting. I think there'll be a lot of intersections there. And then, of course, something that we were doing quite a few years ago is the large-scale simulations of devices themselves, and whether it's a superconducting device or a atom in a solid sort of quantum computer device, they all require a lot of device modelling in order to understand how you get to the error rates that you need to get to. So I think for quantum computing, there'll always be this tight nexus between quantum computing and HPC, and it's going to be interesting to see how this story goes. Thank you very much.
Analog Q gain, if you like, of
oh yes, okay, the economics of it all.
The economic gain of
yes
calculation in terms of the net value of the research generated over the total investment. The estimate was that would not actually be realized to greater than 1 for at least 20 years. So the comment is that, okay, that's a fairly hard restriction. What class of problems do you think quantum computing might actually be able to address on a realistic or early timescale, which is much less than 20 years? And the second part of that question is that I taught a bit of quantum computing in School of Computing. Quantum coding is very different to classical coding, and I suspect there's a lot of people that will require training in that space eventually. So there will be an expansion of, at some point, when it comes online, an expansion of growth required. So maybe the first question is about, when do you think the earliest useful calculation of quantum computing will be applied?
Oh, look, to be honest, I'd be guessing, because I think nobody really knows, and particularly if you put... So I'm a scientist. That for me, until somebody says I don't have enough money, I'm not going to care too much about how much. I just want to know what's possible. That's what I'm trying to find out. And I realise there will be these cost boundaries, and that'll be a very interesting interaction to see how that plays out. There's economics going on right now on how much it costs to access the NISC systems, and the value there is not that we're doing getting real-world solutions from them. We're learning by having access how to optimise programs, and a lot of industry is getting involved in that because the value is to be leading in that and not trying to be a fast follower. Okay, so what sort of problems? I wouldn't be able to say. I mean, chemistry is in the fault-tolerant regime, although with the techniques and the algorithms that we're developing now that are much more balanced with respect to HPC, those algorithms now might lend us to being able to do chemistry with fewer quantum error corrected qubits. So instead of 20 million qubits, it might be a lot less. Optimization is an area that lots of people look at, but it's not clear how big the system would have to be, the quantum computer, to beat a classical heuristic. That's a really hard benchmark to compare against. I think the unknown is going to be quantum machine learning. I think that's a sufficiently murky area that it's very hard to classify, that may actually be able to do things that are quite different to normal machine learning. So that might be the best bet. But irrespective, it's going to be in that region closer to fault tolerance, I think, and it's after people have really looked at how to do quantum error mitigation. On the second point, the training is something that I've been looking at a lot, and that's why we developed that QE system. So when we, the courses that we offer, the subjects that we offer at Melbourne University are not really targeted at quantum physics students. They can do it, but they're really targeted at people with no quantum physics background. That's how we've designed those subjects from the ground up, and having a system like that means that they don't have to multiply Pauli matrices and do all this boring quantum physics stuff. They can actually program and get results out in the first week. So I think that's a really important point, the training, because this is a different way of coding. You know, I do exercises and modules in secondary schools, and they pick it up really quite quickly when they have a system like that. So I think there's a lot of really great stuff that can be done in the educational space, and I think it's very important.
They might at least need first year.
Yes, okay. That is a prerequisite that they've done first year linear algebra. We did try originally without that, and some people were just struggling a bit. Yeah.
With the number of physical qubits versus the quality, there's sort of like I picked up maybe it's a roughly linear spacing of the IBM points. I don't know. There maybe is hints of something like a quantum equivalent of Moore's law. Do you have any thoughts about that in terms of like the progression of qubits?
I don't know about the internal machinations of how that's timed. I think that's probably comes down to a reasonable time frame of developing from now 400 to 1,000. 1,000 is getting to about the limit on one chip. Okay, so I think there'll be different sort of developments after that. Probably one of the things that's underestimated is the time to take to fine tune and calibrate those systems. So the other thing is that these systems are calibrated daily. So every 24 hours there's effectively another set of gate errors and so forth, and it annoys people when your jobs run across calibration and all the rest of it. But I think a Moore's law it's going to be different in all these different physical architectures. So, photonics will have their time scale, spins in solids will have their time scale. It's going to be very interesting to see when there are enough data points, as you're now picking out, to see how that's scaling and if it's a self-fulfilling prophecy or if it's indeed very different for the different systems. Because they'll all be linked by, demand and imperative. So that'll be fascinating. Thank you.